Hello everyone, and welcome to another episode of Coding Adventures. In the past, we've played around a bit with ray tracing, which more and more games lately are starting to make use of, especially for things like shadows and reflections. But the vast majority of 3D graphics is still done with a different approach, known as rasterization. So a simple little software rasterizer is what I'd like to try building today. Nothing terribly fast or fancy, just some humble 3D graphics rendered from scratch on the CPU. So I've started out with this structure here holding 3 floating point values, quite creatively called float3, which will represent the red, green, and blue channels of our colors. These have been mapped to x, y, and z variables, by the way, so we can use it more generally as a 3D vector for positions and so on. But for now, let's just create an image by defining a grid of these float3s, and then loop over every cell or pixel in that grid to assign a color. For instance, here I've just calculated how far along each axis of the image we are, as values between 0 and 1, and then used those as the intensities of red and green. This would probably look very cool already if only we could see it. So let's write our artwork out to an image file. And to do that, I've been looking into this bitmap format, which at least on Windows is the simplest I've come across that can be opened without any special software. We basically just need to write a little header specifying, for example, the width and height, and that we're not bothering with compression today, thank you. And after all that, we loop over our image and write each color channel into the file as a single byte. Okay, let's give it a whirl, and our file has just popped into existence over here. So let's open that up, and it sure looks like a beautiful bunch of bytes, but we don't really want it interpreted as text, of course, but rather as a BIMP. That's looking very promising, although rather less red than I was anticipating. Hang on, let me scrutinize this example I was following. Red pixel 00255, and here's a blue pixel 25500. So it's just backwards. Alrighty then, let's switch that up quickly. And now we have our stunning image. All that remains is to draw some 3D graphics on it. For that, we're going to need some triangles. So over here I've defined 3 two-dimensional points just somewhere between the width and height of the image, and then said that if the current pixel is inside the triangle, it should be colored in blue. This point and triangle function is looking ominously red though, which means we're going to need to get mathematical for a moment. So here are 3 points for us to ponder, and we can draw little arrows between them showing the direction of the segments from A to B to C and back to A. It'll be helpful, I think, to consider each of these as having a left side and a right side, but I get easily confused, so let's tilt our head slightly so that this segment here is standing straight up, and then mark left and right with little arrows. Then, tilting our heads a bit further so that the next segment's standing straight, we can again label the left and right. Okay, one last twist, this side's left, this side's right, and then having spun our heads right round, we're back to where we started. Now, we want to know if a point is inside this triangle, so let's introduce a point P over here, and we can see that it's currently on the right side of 2 of the segments and on the left side of the other. And if we observe as it creeps along the outskirts, we can see how at all times it's on a different side of one of the segments. It's only, of course, if point P finally gathers the courage to dart inside, that the segments now have it completely surrounded, meaning the point is on the same side of all of them. So that's the condition we want to test for. We just need to solve the sub-problem of which side of a segment is the point actually on. So let's picture an arrow going from point A to our point P, and then using the ever-helpful dot product, we can calculate whether these 2 arrows are pointing more in the same direction, where the dot product is positive, or more so in opposite directions, where the dot product is negative. So we've divided space up into above and below, which is kind of the opposite of what we wanted. But to fix that, we can simply rotate one of the vectors by 90 degrees, transforming above and below into the left and right we've been looking for. Alright, so quickly turning these concepts into code, here's our function for the dot product of 2 vectors, which multiplies together their lengths and the cosine of the angle between them. Although the math simplifies wonderfully to just be the product of their x-axes plus the product of their y-axes. Then rotating a 2D vector by 90 degrees is nice and easy. We just swap x and y around and make either one of them negative for clockwise or counterclockwise. building on those two, we then have our point on right side of line function, which just calculates the two vectors we were looking at a moment ago, with one of them rotated by 90 degrees, and then tests whether that dot product is positive. At long last, that brings us to our actual point and triangle test, which checks which side the point is on of all three edges, and makes sure that they are all the same. So we can run the code now, and admire the triangle we've created. I think I messed up the maths. Oh, actually it was the code that got me. I forgot how programming works for a moment there. That is not how you test if three things are equal. Okay, let's run it again, and this time we get perfection. At least for this one specific case. So to test a wider variety, I've quickly set up a whole bunch of randomly initialized triangles. They also have random velocities and colors, and I've set them to just bounce around the screen for fun. Then in our image loop, we loop over each set of 3 points, run our triangle test on those, and of course color in the pixel if it passes. Now we just need to wait for this to render. And finally, it is done. It looks like I forgot to clear the background each frame though, so it's a bit of a mess. Well, I guess I'll render it again then. Alright, taking a look at some of these frames, we can spot a few artifacts like these very thin triangle slivers where there's just not enough pixels in the image to properly resolve it. But what I'm more worried about, jumping forwards a little, is that the background is suddenly completely colored in. Okay, after a little debugging, I discovered that one of the triangles must have somehow collapsed into a single point, which causes our test to malfunction and say that everywhere is inside of that triangle. We could fix this in different ways, but I thought I'd try simply moving that loop we're doing over all the triangles up to the top of the rendering code. The point being that we can first calculate the bounding box of the current triangle, and then limit the scope of the rendering to only the pixels that lie within it. That is both an optimization, we can see the frames flying past now, and it also solves our problem because if a triangle were to collapse into a single point again, then it would have a 1x1 pixel bounding box, meaning it would be drawn as a single pixel, which I think is reasonable. Anyway, I think this is looking good, so enough dawdling in 2 dimensions, let's boldly go where many have gone before and try to draw a cube. First though, we'll need to parse the data in this 3D object file, which is happily quite self-explanatory. We have vertex positions denoted by V, then some vertex normals and texture coordinates, which we can worry about later, followed by a mysterious S, the significance of which I've not yet ascertained, before finally the face indices. So I believe this means that we take vertex positions number 1, 5, 7, and 3, and that will be our first face. Although 4 points is famously not a triangle, so we'll have to do that conversion ourselves. And here's what I've come up with so far. We just go line by line through the file, reading in all the points, and adding them to a list. Then once we get to the faces, we just read in each point index, and add the corresponding point to this list of triangle points. If there are more than 3 points in a face, then we can just make a triangle fan like this. So no matter how many points there are, we just take the first 3 as our first triangle, and then when we add in the 4th point, we'll first append another copy of the first point in the face, and the last point from the previous triangle, and so on until the whole thing is filled. This is assuming that the faces have the decency to be convex. If we wanted to handle concavity, then we'd need something slightly more sophisticated, like the ear clipping algorithm. But anyway, here's the setup now. We load in our cube data, generate some random colors for the triangles, and store that in this model class. Additionally, we create a render target to draw to, which is nothing fancy at all. It just holds an array of colors exactly like the image we made before, and gives convenient access to its width and height. The model class is even less interesting. Now, this data can then just be passed to the same rendering function we had for our triangle soup earlier, although it is panicking at the moment because the triangle points are now 3-dimensional, and it has no idea what to do with that. So let's help it out by first passing the points through a function that converts them into the familiar 2D pixel coordinates, which we can refer to as screen space. Now, if we imagine our vertices being somewhere out in the world, which might be measured in meters or whatever, we'll need to define how many meters fit into our image. I've chosen 5 for no particular reason, so that we can then figure out a conversion factor between meters and pixels. If we then fiendishly flatten 3 dimensions into 2, by just pretending that z doesn't exist, we can convert that to pixel units, and finally add it onto the screen center, just so that a point at 0 in the world maps nicely to the center of the screen. Okay, let's run this quickly. And at last we can behold our beautiful box. Well, a single side of it anyway, so let's maybe get it spinning around so that we can appreciate it from every angle. Consider then the x, y, and z axes of our world, pointing perhaps rightwards, upwards, and forwards. If we want our cube to spin around the y-axis, for instance, we'll need to create a new set of vectors that describe what rightwards and forwards specifically mean to our cube, or whatever object we're rotating. I find it helpful to think of these vectors as little points just moving around a unit circle, and for any given angle we can describe them using sine and cosine like this. So imagine now that our model has one of its vertices over here, for example. We can apply the rotation to that vertex by simply taking its x-coordinate, 1.8 in this case, and going that many times along the model's own x-axis vector, which I'll refer to as I hat, by the way, just to differentiate it from the unchanging x-axis of the world. Okay, next we take the y-coordinate, so 0, and move that many times along j hat, and finally the z-coordinate, 0.5, and move that many times along k hat. And here's where the vertex has ended up. So if we now continue increasing the angle, we can see how that point, of course, rotates along with its basis vectors. Okay, I've made this little transform class now, which holds a variable for our angle around the y-axis, called the yaw, and it has a function for applying that yaw, and whatever else we want to add later, which we can think of as moving a point from its local space within the object to its true location in the world. This works, as we've just discussed, by calculating a set of basis vectors using sine and cosine, and then moving each coordinate of the given local point along the corresponding vector, which is done over here. Then I've simply added this transform to the model class and set the yaw to decrease a little every frame to test it out. So why is nothing happening? Oh, right, you have to actually call functions for them to do something. So when we're transforming each vertex into screen space, we'll now first want to transform that local vertex point into world space by applying the rotation with our little function, and then we can convert that into screen space like before. Alright, let's run it again, and this time it is actually doing something, and it's looking great. Never mind, I spoke too soon. Okay, clearly the far side of the cube is rendering in front as it rotates around, since we're just drawing each triangle on top of the last, which somewhat spoils the effect. So let's revisit our triangle mass for a moment, and here we can see again our point P on the right side of all of the segments, but if we rotate this triangle around, suddenly it appears that the point is on the left side of all of them. So assuming that the triangles in our models are all wound in a consistent order, be that clockwise or counterclockwise, we can tweak our code to cull this backface case by only registering the point as inside when it's on one specific side of all of the segments. Okay, so now with only the front faces showing, first of all it renders a bit faster because it's not wasting time filling in those back faces unnecessarily, but more importantly it's now looking correct from every angle. Well, we can't actually see the top and bottom yet, I suppose, so let's quickly add in a second axis of rotation. For that, we could just calculate how the up and forwards vectors rotate around the red rightwards vector. Let's call that pitch, and obviously that's again just simple sines and cosines to get us our I, j, and k hat for this new rotation. What I found confusing at first though is, what if we've already applied some yaw? How do we then make the pitch now rotate around this new orientation of the rightwards vector? But in fact, we've already figured this out, because we wrote this function here that takes in a set of basis vectors describing what we want right and up and forwards to mean, and then transforms some input vector along those axes. So far, that input vector has just been our vertex positions, but if we now calculate the vectors for pitch, simply ignoring the yaw entirely for the moment, we can then afterwards take each pitch vector and transform it along the yaw vectors. This will give us a new set of vectors describing the effect of first rotating around the vertical axis and then rotating around wherever the horizontal axis ended up after that. So trying this out now, I'll first apply some yaw, and then apply some pitch. Hang on. Okay, I got a little mixed up with the minus signs. While we're back here though, I quickly want to mention that we could of course work through these calculations and simplify things quite a lot. Or even just use some neater notation, like each of these could be the columns of one matrix, each of these could be the columns of another matrix, and then this here is just multiplying the two matrices together. But I find it helpful to write everything out like this to understand what's going on, and then we can always tidy up and optimize later. Anyway, let's see if this is actually working at last. So I'll do some yawing and some pitching, and that's looking pretty good. One thing that is lacking at the moment though is a sense of perspective, which is where things far away look small while things nearby look really big. You may have noticed this before. So when we're calculating the number of pixels per world unit, that value should actually vary based on how far away the object is, since if it's further away it'll obviously cover fewer pixels on the screen. So to achieve that, we can try simply dividing by the z component of the current point. Then I've also quickly added a position vector to the transform class, by the way, so we can move our cube around, and this just needs to be added on once we've applied the rotation to a vertex, so that all the model's vertices will be centered around that position in the world. Okay, let's give it a go, and we can see that to start with things are a little funky if we rotate the cube around, since it's centered at 0, meaning that some points will have negative z values that we're then dividing by. But if we move the cube a little ways forwards to prevent that, we can rotate it around and see that it is indeed in glorious perspective. The perspective is maybe a touch on the extreme side though, so let's think about how we can control it. Say this point here represents our sort of imaginary camera through which we're viewing the world, looking forwards along the z-axis. What we want is to be able to define its field of view, which is to say how much of the world it can see at once. Like here we have a 20-degree view angle, which is fairly narrow, so we're zoomed in on just a small section of the world, whereas 120, for example, would be pretty wide. Let's go for something in between. Then I want to bring our cube into the scene, and let's divide each of its vertices by their own z-coordinate, like we effectively just did in the code, which gives us these projected points over here, all unsurprisingly 1 unit away from the camera on the z-axis, since z over z is 1. Now, we could think of this plane that our points have landed on as the screen or image that we're rendering to. And we can see that if one of the vertices of our cube goes outside of the field of view, its projected point has now gone off the top of the screen, and would of course no longer be visible. But if we just increase the field of view a little bit, now it's back on the screen and of course visible once again. So the world space height of this screen here is obviously dependent on the field of view, and we need to calculate it so that we can replace this arbitrary constant in our code with the more intuitively adjustable field of view value. With a touch of trig, this is not too tricky because we have a right angle triangle here with an angle we know, that's just half the field of view, and a side length of 1, and this is our unknown half of the screen height. So it's an opposite over adjacent kind of situation, meaning we can plug into the code that the screen's world height is equal to the tangent of the field of view over 2 times 2. Running this now with a vertical field of view of 60 degrees, I think the perspective is looking a lot more natural. To play with the effect of our fancy new field of view a little, I've quickly hacked in some temporary code which constantly recalculates the field of view based on the cube's current z value in order to try keep it the same size on the screen. And with that active, if we now move the cube closer to the screen, we can see the perspective getting more intense as the field of view widens to keep it the same size. And if we move the cube further away instead, now it begins to look flatter and flatter as the field of view narrows to zoom in on it. In fact, it pretty much looks like what we had originally, which is known as an orthographic projection. Let's put things back into perspective though. Now, cubes are great, I love cubes, but let's try rendering something a little more sophisticated, such as Blender's little built-in monkey. Exporting her gives us this rather long list of numbers, but we can simply feed them to our parser of course, and Bob's your monkey's uncle, out pops Suzanne. Somewhat distressingly though, her ears and brow ridges are rendering right through her head, so our trick of not drawing the back faces of triangles obviously falls short with this more complex geometry. we'll want to keep the culling as an optimization, but for a more robust solution, we're going to need to track how far away each pixel is that we draw, so that we don't overwrite things nearby with things further away. To that end, I've tweaked the world to screen function once again to return a float 3 now, with the first 2 dimensions still just being the pixel coordinates, but the third telling us the depth of the pixel, which is just how far away it is on the z-axis. Problematically though, this tells us only the depths at the 3 corners of the triangle, while we need to know it for any pixel inside, which means, lucky us, it's time for some more triangle maths. Now obviously if the pixel we're drawing is all the way over at point A for instance, then the depth would just be the depth at A. But if the pixel is halfway between A and B, let's say, we'd need to blend between those 2 depth values. More generally, what we're looking for is a set of 3 weights, telling us for any location what proportion of depths A, B, and C would need to be mixed together. So for the weight of depth C, for example, we'd need some quantity that gets bigger and bigger as the pixel approaches point C, but smaller and smaller all the way to 0 as it approaches either A or B. Well, something that fits those criteria would simply be the area of this triangle here from A to B to P. Clearly, that gets bigger and bigger as the pixel goes towards C, covering finally the entire original triangle, but is reduced all the way to 0 if the pixel goes to either other corner. So that's perfect, and it's probably no great mystery then what we'll be using as the weighting factors for the other 2 corners. For corner A, it would just be the area of this little triangle, and for corner B, the area of this other little triangle. So having arrived at this concept, the specific maths problem we actually need to solve is just, given any 3 points, what is the area of that triangle? As a starting point, we can see that 2 copies of the same triangle can be joined together to form a parallelogram, which, like a regular old rectangle, has an area of base times height. So our triangle must have an area that's exactly half of that. Putting on our trig goggles again, we can spot that this height value is equal to the length of this segment here, multiplied by the cosine of the angle between it and the direction perpendicular to the base. So let's picture rotating the base by 90 degrees, and now we can just take the dot product of this perpendicular base vector with the other vector here, since remember that this has the effect of multiplying together their lengths and the cosine of the angle between them, giving us the base times height that we're looking for. Typing that up into code, we get this, which is by the way a signed area, meaning it ends up being positive or negative depending on the points being given in a clockwise or counterclockwise order. You might have noticed actually that this is pretty much identical to the code from earlier for figuring out if a point is on the right side of a line segment. We can see now how that's just calculating the area of the triangle formed by the segment and the point, or parallelogram really since we don't divide by 2, and then it's testing if that's wound in a clockwise direction. I wasn't thinking in terms of area when we wrote this though, so I didn't connect the dots until now that we've just implemented the same thing again. Well, alright, let's delete this function then I guess, and of course our point and triangle function is complaining bitterly, but I'm going to rewrite that quickly. And here's the new version. It calculates the signed areas of those inner triangles, and figures out whether the point is inside the triangle by checking that they're all clockwise, so exactly the same as before. Those areas can then also be repurposed as the weighting factors we've just been talking about, although one extra detail is that we're dividing each by the sum of all 3, just so that they're neatly normalized to add up to 1. Alright, to put this to use, I've added a grid of floats to the render target as a sort of special image purely for keeping track of the depths. So its values will be initialized to infinity each frame, and then when we're rendering, we can first calculate the depth of the current pixel by multiplying the depth at each corner with its associated weight, and adding those all together, which is yet another dot product. We can then compare that to the value currently in the depth buffer, and if it's further away than whatever's been drawn here so far, we just skip it. But otherwise, we draw in the pixel's new color and depth value. Alright, with that done, let's observe the monkey, and she is looking wonderfully solid. Just for fun, let's also render out the depth map quickly to see what that's looking like. Okay, with this implemented, we should now be able to correctly render multiple objects. So I've quickly added our little cube back in, and it's looking pretty good, except for this sliver along the bottom here slicing through Cezanne. I'm pretty sure this is the bottom triangles of the cube misbehaving due to having 0 area when projected onto the screen. So I guess we can fix that by just changing all these area checks here to be strictly greater than 0. And now the line has disappeared. Unfortunately, so too has the middle of our monkey's face. Well, I didn't really think that through. What we really care about is the total area not being 0, since that messes up our weights when we do the division. So let's tell it to ignore the triangle if it has 0 area like so, and now that seems to be working just fine. Okay, I've quickly thrown in a handful more cubes to make this simple little test scene here, and I'm longing to just step inside and have a look around. So writing our results out as image files has been a nice minimal way to get started, but I'd like to now switch to real-time rendering instead. And I'm just going to go with the easiest approach I know, which is a lovely little library called Raylib. This has loads of great features that we'll be completely ignoring today, because all we want to do is open a window and shove our image onto it. I've also taken this opportunity to clean up the code a bit, by the way, basically separating it into a scene, which is responsible for loading in models and moving them around however we want each frame, and then the rasterizer itself, which takes in the data from the scene, just a list of models, and actually renders it. So running this now, we can see our little window pop up and render in real time. Very exciting. The whole point though is to be able to move around in here, so I've created now this camera class which holds the field of view and, more relevant to our purpose, a transform for the camera. This means that when we're updating the test scene, we can just listen to some keyboard input to control the camera's position. For this to have any effect though, we need to take the world point of each vertex and convert it now into view space, which is like if we imagine moving the camera back to 0 while dragging the rest of the world along with it. To do that, I've made this little function here, which simply subtracts the transform's position from the given point. It should also reverse any rotation stored in the transform, but one thing at a time. So let's launch the game to try it out, and I'll start by moving the camera along to the left, and we can see how the world appears to move rightwards in response. And then let's go back to the middle and head forwards. Things unfortunately seem to be falling apart a bit now, but I'm pretty sure what's happening is that points are ending up with negative z values as they go behind the camera, which, as we noticed earlier, causes all sorts of nonsense when we do the perspective division. So let's try simply checking before attempting to render a triangle if any of the depths are sub-zero, and if so, just skip that triangle. And running this now, we get a flawless result. Still, it's better than having the triangles blow up all over the screen, though we will of course have to come up with a more sophisticated fix at some point. But for now, I just really want to be able to look around with the mouse. So I've added some mouse input handling here to just update the pitch and yaw of the camera, and also tweak the movement so that pressing forwards, for instance, moves along the camera's own forward vector. We will need to head back to this little function here now to not only undo translation, but also reverse rotation, so that the whole world will rotate opposite to however we rotate the camera. Let's maybe copy over the local to world code and try to do everything backwards. So rather than first applying the rotation and then the translation, we'll first undo the translation and then undo the rotation by calculating a set of inverse basis vectors. I think we can just calculate these the same way as the regular basis vectors, except with pitch and yaw being negative, so that it goes in the opposite direction. Alright, trying this out. It almost works, but our view is swaying somewhat sickeningly from side to side like we're out at sea. So to reverse the rotation, we can't just negate pitch and yaw, we also need to apply them in reverse order. Like when we rotate something, we're first applying the yaw, and then applying the pitch. So to undo that, we'd obviously need to now first apply the negative pitch, and only then the negative yaw. In the code, this just means using the pitched axes here to transform each of the yawed axes, rather than the other way around. Or in terms of matrices, as I mentioned earlier, this would just be swapping the order in which we multiply them. Anyway, we can now look around without wobbling. Truly a great day for landlubbers. Now, I think this solution we've come up with is nice in terms of conceptual clarity. We're literally reversing our calculations, but there is a much more elegant approach I've come across in the past. The way this goes is to just calculate the regular basis vectors and then swap things around so that I hat is equal to the first component of each of them, j hat is equal to the second component of each, and you guessed it, k hat is equal to the last component of each of them. And would you look at that, it doesn't work at all. Okay, silly mistake. If we modify I hat here, then of course that modified version gets used in the next calculation and so on, which is not actually what I was going for. So I'll just make new variables for each of these to fix that. In matrix terms, in case you care, we're simply swapping around the rows and columns here to give us the transpose of the original matrix, which turns out to be a shortcut for inverting the matrix in the special case of pure rotations, where our three basis vectors are unscaled and at right angles to one another. Anyway, more importantly, we can see it's working identically to our original solution, just a lot more clean code-wise, of course. Now, this disappearing floor is bugging me quite a bit, but I'm not quite sure how I want to tackle it yet, so let's simply sweep it under the rug for the moment by subdividing the model several times, meaning that when we look around, the offending triangles are typically out of sight when they get culled. I have noticed another issue though with objects that are close together, such as this dragon and the floor. We can see how what gets drawn on top is shifting ever so slightly as we look around, so clearly there's something slightly suspicious going on in our depth calculations. Let's have a look then at this ruler, the middle of which is over here, halfway, believe it or not, between the top and the bottom. However, if we change our point of view a little, we can see that the midpoint over here is in fact no longer halfway between top and bottom, at least not if we're thinking of those as just points on our two-dimensional screen. And that's exactly the trouble with our current implementation. We're projecting the three-dimensional triangle points into 2 dimensions by dividing by the depth at each point, and then we use those 2D points to derive the weights for interpolating between the depth values. So seeing as the two-dimensional points are squished closer and closer to 0 the larger the depth happens to be, we need to apply the same squishing effect to the depths themselves before we can sensibly blend between them in 2 dimensions. And so let's take 1 over each of the depth values here to do that. It doesn't actually matter if it's 1 or some other constant, because once we have our squishified depth value for the current pixel, we'll simply reverse that operation to get back the actual depth value. Alright, trying this out in our test scene, we can see that the dragon is no longer bobbing about, but instead has its feet planted firmly on the floor. That's very nice, but I am getting a little sick of staring at these randomly colored triangles, so let's see if we can perhaps apply some textures to our models. Earlier on, we noticed these texture coordinates in our OBJ files to help with that. And the idea is just that for every 3-dimensional point in a face, there should be a corresponding 2-dimensional coordinate between 0 and 1, describing where that point lies on an image, or texture. So I've tweaked the loader quickly to read those coordinates in, and then set up the rasterizer to now interpolate them as well, inside of each triangle. We will need to do some perspective correction for these two, but I'm just curious first to see what it looks like without it. Then I've also set up a very crude kind of concept of a shader, since we might want different objects rendered in different ways, like with textures or without, for instance. So here is a tiny texture shader, which simply returns the color of its assigned texture at the given coordinate. And to help with that is this new texture object, holding a familiar grid of colors, which can just be loaded in from a file, of course, and it allows that image to be conveniently sampled. In this case, just converting the 0 to 1 coordinates to actual indices for a very simple nearest neighbor sampling. Let's see how that looks. Alright, not too bad, but we do indeed have some strange distortions taking place for the exact same reasons we saw before with the depths. So let's fix that quickly, and it's just the same idea again. We need to divide each texture coordinate by the depth at its vertex position so that they get squished just like the points themselves, meaning, once again, that we can interpolate between them sensibly in 2 dimensions. And then afterwards, we want to undo the squishing to get the actual coordinate, and so we just multiply by the depth of the current pixel. Alright, giving that a go now. It's looking great, so let's slap on a slightly snazzier texture to celebrate. We should probably test this on something slightly more complex than a cube though, and that is looking pretty tasty. It is also looking quite flat, however, since we haven't yet invited light to the party. So to fix that, I'm going to start by quickly loading in the normal vectors that are also stored in our OBJ files, which just tell us what direction the surface is facing at each vertex of a model. We'll then want to interpolate these across each triangle, like we did with the texture coordinates, because even though triangles themselves are flat, allowing the normal to vary across the surface lets us fake a low-resolution mesh looking a lot smoother than it really is. So this normal vector is then passed to each shader as an additional piece of information, and I've made a little lit shader now for us to do some simple lighting in. To begin with, we should technically actually normalize the normal to ensure it has a length of 1 like any respectable direction, because it can become a little disheveled during the interpolation. This is done by calculating the length of the vector via Pythagoras and then dividing each of its components by that length. So each component is guaranteed to now be somewhere between negative and positive 1, so we can display it nicely as a color, just to check that everything's working properly, by adding 1 and then halving the result, which makes each component be between 0 and 1 instead. Here's what that looks like for flat shaded normals, which is where the normals of each triangle do all point in the same direction. And here's what it looks like with smooth normals, where they're allowed to point in different directions across the triangle. This is all looking perfectly normal to me, so let's move ahead with our simple lighting. And for that we should take a moment to contemplate this little beam of light, which happens to be hitting some surface over here. Now, when the surface is facing the light source, it of course receives the maximum amount of light, whereas if it tilts away, it obviously receives less and less of it. But how much less exactly is what we need to know. So let's say the surface has a width of 1 for simplicity, in which case the fraction of light it receives for a particular angle is just equal to the length of this bottom side here of this triangle. Trigonometry then once again tells us that the length we want is equal to the cosine of this angle here divided by the length of this side, which we defined as just being 1. So all we actually need is the cosine of that angle, which we can get, perhaps you've heard, from the dot product. So if we take the unit vector pointing along the surface and dot it with the unit vector pointing along here, we'll have our answer. Or to make these vectors a little more intuitive, we can imagine rotating both of them by 90 degrees, giving us the normal vector of the surface and the direction pointing towards the light source. Therefore, in our shader, I've added a setting for the direction towards the light and dotted that with the surface normal to calculate the proportion of light hitting the surface, as we saw. This will be negative if the light is pointing away from the surface, so it's worth just clamping it to 0, since negative light doesn't make much sense. But we can then output that as the color of the pixel, and just like that, our dragon is lit. This lighting can look a little harsh though, since in reality light bounces around and illuminates darker regions, as we saw in the ray tracing episode of course. Doing this sort of thing in a rasterized renderer is not easy, so for now we can just crudely fudge things if we want, for instance by remapping the dot product from negative to positive 1 to be between 0 and 1 instead, and that basically just brightens things up a bunch. Now, if we just smush our lit and texture shaders together into a lit texture shader, we can see that the cake from before is looking tastier than ever. I'm happy to announce, by the way, that there'll be free slices at the end for everyone who likes and subscribes right now. First, though, I want to set up another simple test quickly, and I think it'd be fun to bring in this little fella that I made about 10 years ago. Obviously, we don't have support for animations yet, that's a whole other can of worms I'd imagine, so I've just placed him in a fixed pose of wonder and astonishment. Here's what the model looks like unwrapped, by the way, and it just has a super simple texture map with some blocks of color for the skin and clothes. I also figured he'd appreciate a companion on his adventures, and who better, I reckon, than this remarkably ravenous fox from my old ecosystem experiment. So I've set the two of them up in a little scene here, along with our trusty test dragon, and a random tree or two. These are all being rendered with our wondrous new lit texture shader, And I also quickly added a scale setting to the transform script, because I must have modeled the fox with slightly different units in mind. That just means in the code that we have to multiply each basis factor by the corresponding scale factor, so that the vertices are moved to a greater or lesser extent along those directions. And for completeness in our inverse function, we should also then undo that scaling. Alright, let's see how it's looking with the scale applied. So here we have boy and fox together, looking on in awe at the green dragon in front of them. I think it's really cool that we can render little scenes like this now, although obviously there is still so much to be done, like shadows and optimizations, fixing the flickering floor and so forth. There's no chance we'll get to everything today, but I would at least like to have a go at this floor problem. So remember, the trouble we ran into is that when a vertex of a triangle goes behind the camera, in other words it has a depth of 0 or less, we can't divide by that depth anymore without causing a mess. A sneaky idea we could try though is simply clamping the depth value so that it's forced to be above 0. That might not seem like it should work, and indeed it absolutely does not. Speaking of absolutely though, my next brainwave was to take the absolute value instead. That way the depth will always be positive without us having to cut it off anywhere. This went about as well as you might expect. What we're looking at here is actually a slight variation of that idea, using the magnitude of the view position as the depth, rather than just the absolute z. The result is pretty similar, but this one has a nice funky sort of spherizing effect. Anyway, these desperate attempts are clearly not going to cut it. Instead, what we're going to have to cut is the triangles themselves. So when a vertex crosses over the boundary into the forbidden lands, we'll just lop off the tip, which leaves this little quadrilateral here that we'll then have to turn into a pair of triangles on the fly. Another situation that could occur is that two of the vertices could cross the boundary, and in that case we only have to form a single new triangle. Or obviously, if all three are beyond the boundary, then it's a lost cause and we'll abandon it entirely. So each model now holds a list of rasterization points. I don't really know what to call them, but it's just the screen position of each vertex, along with the corresponding texture coordinates and so on. Then each frame we run through all the triangles in the model and calculate their view space positions so that we can test which of their depths are below our clipping threshold. After that, we can count up how many vertices will need to be sliced off, and if that number is 0, then we simply add the 3 points to the list without any modifications. However, if one of the vertices does need to be cut, in that case we'll calculate where along each of the connecting edges the depth cutoff occurs, first as a fraction between 0 and 1, and then using a linear interpolation to get the points themselves, which we can use to create our two new triangles. By the way, we're passing the fraction values in here, so that when we add in the texture coordinates and normals for those new points, we can just do some more interpolating to figure out what their values should be. Now, slicing off two vertices instead of one is just more of the same sort of code, so let's head straight to the results. Here, by the way, we're back to using just two triangles for the floor, none of that subdivision trickery from before, and as you can see, it's working beautifully. Alright, fine, my first attempt was a total disaster, but by about the 10th attempt I finally had it working nicely. The colors here is just some debugging I was doing for the different triangle split cases, so green and magenta are where it splits into two triangles, and yellow is when just a single new triangle is formed. Anyway, I'll remove those debug colors quickly so that we can verify that the texture coordinates are working properly as well. And that's looking good to me. Alright, we've come a long way, so let's do something fun to celebrate. And by fun, I'm referring of course to procedural terrain generation. So this code I've been working on here just calculates an elevation value given some point in the world, which it does using layers of simplex noise with increasing frequency and decreasing amplitude. Then this function here generates a grid of points, jiggled slightly for some variation, and with elevations calculated in a shocking twist by our calculate elevation function. Finally, we have this function here for actually assembling the mesh triangles from that grid. By the way, I've stored the average elevation of each triangle in the texture coordinates, which obviously wouldn't be helpful for actually sampling a texture, but we can get creative and store whatever arbitrary data we want in there. So here's what our mountainous mesh is looking like at the moment. Not too bad, I'd say, but a bit bland in the color department. So let's liven things up with a special new terrain shader. In here, we've got a few floats defining the elevation range of these color bands. And then for every pixel, we do a simple loop to search for the appropriate color based on that triangle's height from the texture coordinates. And now that is looking much more lively. It is a rather small chunk of terrain though, so I've also quickly been setting up a simple system to generate new chunks as we move around, making the terrain effectively infinite. With that in place, we can now fly around to our heart's content. At approximately 5 frames per second, that is, which my heart is not particularly content with. So I've been doing some quick optimizations, like for instance, whenever a transform has its rotation modified, it now stores the resulting basis vectors, rather than having to recompute those over and over for every vertex. I also tried to optimize the triangle test, which did speed things up a bunch, and even came with a funky free side effect. Following that huge success, I left some aggressive suggestions to the compiler in several spots, and flattened our color and depth buffers into one-dimensional arrays, which tend to be a bit faster to work with. I also made this giant array of objects for helping with some tremendously crude parallelism that I have planned in our rendering loop. I'll need to think about how to do this better in the future, but for now, when it comes time to write to a pixel, we place a lock on its corresponding object so that any other threads trying to access it at the same time will be forced to wait their turn. And now our little scene, containing a few 100,000 triangles, is running wonderfully smoothly at about 90 frames per second. Of course, this is on a 960 by 540 window, which is rather minuscule, so we should calibrate our enthusiasm accordingly. Anyway, what this scene is definitely missing is a little plane to zoom about in. So I've gone ahead and modeled one here, but it itself is missing a pilot and passenger at the moment, so I'll need to fix that. And of course, they can hardly go anywhere if the propeller isn't spinning around on the front. So I've quickly gone and added the last missing axis of rotation, a roll around the z-axis, which will allow the propeller to spin and the plane to tilt as it turns. Then we'll want the pilot and passenger and propeller to all be parented to the plane so that they automatically follow its every movement. For that, we can give the transform an optional reference to a parent transform, and when it comes time to actually transform a point, it can first apply its own properties as before, but then pass the point along to its parent, if it has one, to apply its own properties as well, and so on recursively to the grandparents and great-grandparents until the end of the line. So let's try now saying that the pilot's parent is the plane, and see how that goes. Okay, it's a little odd looking, but fundamentally seems to be working. And with a few slight adjustments, we've got something now that's closer to what I had envisaged. The propeller is even spinning around, and since it's parented to the plane as well, we can see how it inherits that rotation as it turns. Truly remarkable technology. Alright, there's just 2 tiny things I want to do before we call it a day here. Firstly, in the terrain shader, if we take in the depth of the current pixel here, that can then be used to blend the terrain towards the sky color in the distance, for a bit of an atmospheric effect. And secondly, I think it'd be cute to have some little clouds floating around, so I've just set up a system to spawn some blobby meshes in the vicinity of the player, and these scale up and down over the course of their lifetime, and once they've disappeared are just recycled in some other location. Alright, I think that is all, so hold on to your hats, because it's finally time to fly away. I'm quite happy with the progress we've made here, but I just want to take a minute to think about the main things I'd still like to do if we return to this in the future. I think support for transparency would be nice to have, so we could make these clouds slightly see-through for instance, and shadows for sure would be great to have as well. These things are fairly expensive though, so putting some proper thought into optimizations would definitely be wise. Also, I've just noticed that the lighting on the plane is not actually changing as it turns, since it somehow slipped my mind to transform the normal vectors into world space, so that's at least one bug that needs to be fixed, and knowing me there's probably many more. Then there are other odds and ends, like it would be nice and neat to represent our transformations and the camera projection with matrices, maybe add support for a vertex stage in the shaders, and textures certainly need some attention too, with more sampling options and MIP mapping and so on. There's certainly plenty to keep one occupied. But that is going to be everything for today, so thank you for watching, let me know if you have any suggestions for the future, and until next time, cheers.